All creatures finally die. Usually their bodies decay and disappear into dust. But sometimes they leave behind them something that may last millions upon millions of years. When you pick up a fossil, you're holding a piece of a lost world. What did that world look like? Did it have flowers and warm sunshine? Or was it cold and frozen? Or covered in water? Or was it harsh and empty, a desert world? Everything we know about the past, like the dinosaur age or the age of fishes or the ice ages, has come from rocks and fossils. Each of these skeletons is a detective story in which the fossil had to be first freed from its prison of stone and often painstakingly put together like the pieces of a jigsaw puzzle. Yet this is only the first step. A fossil is a trace of a living thing in the rock. But what did it look like when it was alive? That's why dinosaurs are so impressive. We can imagine what a T-Rex looked like. We can imagine its size and strength. And we want to know more. What was the world of the dinosaurs like? What happened to them? This program is about how we build that bigger picture. Here's a fossil from an age even stranger than the dinosaurs. But because it comes from a time when creatures were smaller and more primitive, it's less well known. However, the humble trilobite has a strange and useful tale to tell.
Trilobites are really beautiful, and you can see how they got their name. 3 lobes to the body. 1, 2, 3. Now, trilobites are much more common fossils than dinosaurs, and that's the first key to unlocking the past. Some creatures fossilise much better than others, and trilobites had a hard shell. In fact, they're ancient relatives of crabs, lobsters, and believe it, insects. Hard parts, like a shell, take a lot longer to rot away than soft parts. That's why, in the right rocks, trilobites are very easy to find. They had a shell, and they lived in the best place to be fossilised, the bottom of the sea.
The world of the trilobite began 540 million years ago. Here in the early Cambrian period, all life is still where it began, in the sea. No animal has yet crawled ashore. Above and below, the sea looks much the same as today. Although there are no modern fish, they're still 130 million years away. This is a world of algae, jellyfish, worms, and sponges. Trilobites crawl across the bottom and burrow in the sand. The sea is shallow and sandy. A dead trilobite, or a trilobite shell, soon becomes covered in sand and buried. If it lies undisturbed for long enough, if it becomes buried deep enough, the sediments around it compress and cement together into stone. The trilobite has become a fossil. Creatures made up of soft parts have much less chance of becoming fossils. They usually rot or squash in the sediments, leaving no trace. Yet there is a faint chance that their impression will be preserved. If any fossil survives long enough, the dissolved minerals that are helping to cement the sediments into rock may also gently replace it with a perfect mineral copy. The fossil, like the sediment around it, becomes turned to stone. In this form, many creatures have left a trace through immense periods of time.
All these trilobites are mineralised copies of the original animals. They're stony. For example, we can see where this one's been cracked right from the rock. There's no way any original trilobite material could survive over 500 million years. Time and an active Earth destroy fossils all the time. So, recent fossils are more commonly found than ancient fossils. Things which had hard parts are more commonly fossilised than those which had soft parts, and organisms which lived in water make more fossils than those which lived on land. So in other words, not all life in the past had an equal chance of becoming fossilised.
Water offers the best conditions to make a fossil. Why? Because water carries the sediment and dissolved minerals, which are the ingredients of rocks like these. These are sedimentary rocks. Sedimentary rocks can be built on land, from sand dunes for example, but the most common ones are formed under the sea or in lakes and rivers. Not surprisingly, most fossils are formed on the bottom of the sea. Of course, to find marine fossils on dry land like this, something must have happened to raise the rocks or lower the sea, or both. Sometimes the whole rock may be made of fossils. This whole cliff is the remains of an ancient coral reef. And this thick black stratum is coal, the remains of plants that once grew in swamps millions of years ago. But coal also shows what can happen as the deposit is buried even deeper. Heat and pressure break it down, turning most of it to pure carbon. Fossils are rarely found in coal because they're destroyed as it compacts into a hard black mass. But even when fossils are abundant, building a picture of their world isn't easy. For example, from the number of their fossils, you might easily think that trilobites were the only animals in the Cambrian Sea, but they weren't. If we look closer, there are clues to their environment.
Take our humble trilobites. Since they're obviously very similar to crabs or shrimp, we can guess that they must have lived in much the same way, as scavengers or predators of smaller creatures. They grew by molting their shell. Many had highly developed compound eyes on their upper side, and we know from insects which have similar eyes, this would have made them extremely sensitive to movement. Also, we found trilobites rolled into a ball, with their spines sticking out. It looks like they needed to be able to see prey as well as defend themselves from predators. There must have been some kind of predator, something which ate them. Also, these eyes suggest to us that they used to live in shallow, well-lit waters. So, even without any other Cambrian fossils, we've started to build a picture of the world of the trilobite.
The most useful fossil finds are where wider evidence of the lost world can be found. In a very few places, such as here at Kangaroo Island, soft-bodied Cambrian creatures were fossilised along with trilobites. At last we get a glimpse of other strange creatures which lived in what was clearly a rich ocean, from early versions of sponges to this large swimming creature with powerful jaws. Was this the eater of trilobites? Another example of a fossil find that builds a bigger picture is in Queensland at Lark Quarry. Here the tracks of dozens of dinosaurs were preserved in mud as they stampeded away in fear of the arrival of a meat-eater. These are known as trace fossils. Fossils not of the creatures themselves, but their trace. These prints are clear indication that some dinosaurs lived in herds. But the biggest picture of all is the picture in time. Where rock strata have built up high, we may see sequences of fossils. The time required to build all this was many millions of years. And of course, the oldest rocks are at the bottom. And we often find that fossils at the bottom are of more primitive organisms than fossils higher up. If trilobites, for example, were found in the lower rocks, dinosaur fossils would only ever be found in younger rocks higher up. The strata reveal change and evolution in the history of life. Of course, no one set of strata shows the complete story. But the big picture can be built by comparing fossil sequences from different locations. Location A may have a sequence of trilobites below two non-fossil bearing layers, with a layer containing bivalve shells at ground level. Location B may contain the same kind of bivalves, but this time near the bottom, with ammonite and dinosaur fossils in a layer higher up. By matching these sequences, we can build a bigger picture of fossil order than at a single location. The extension of this process by scientists over many years has led to the geological timescale. So, for example, we can answer the question, did humans ever see a live dinosaur? The answer is no, because human fossils are found in rocks at least 65 million years younger than any dinosaur fossils. The geological timescale is vital to understanding fossils. This amazing fossil site is at Riversley in Queensland. All the overlying strata have long been worn away, and these rocks are simply left as outcrops. But we can still date the fossils using the timescale. These are 25 million years old, from the age of mammals. Australia also has some of the oldest fossils in the world. They're called stromatolites. Telltale layers of calcium carbonate were deposited by bacteria that slowly built these nodules. This fossil is 3.5 billion years old. What did they look like? Amazingly, stromatolites are still around. These are living stromatolites. In Shark Bay, Western Australia, a world of the past still continues. It shows that if an environment stays around, its life forms may survive too. This is why creatures in the sea have altered less than creatures on land. The sea is a relatively stable environment.
This is a shark tooth from 60 million years ago. As you can see, it looks just the same as a modern shark tooth. This tells us sharks haven't changed much over time. Sharks, of course, are still around. And judging by the size of this old tooth, this shark must have been a whopper. Trilobites, however, are no longer around. The big picture for the trilobites is they died out as part of a great mass extinction just before the arrival of the dinosaurs. But what caused this so-called Permian extinction, which wiped out 90% of all living things? No one knows. Perhaps it was similar to the disaster nearly 200 million years later, which we think finished off the dinosaurs.
Paleontologists are scientists trying to understand fossils at three levels. First, to recreate the creature itself, then to understand its world, then to fit it into the picture of time and evolution. Of course, humans are in the picture too, as the latest chapter in a great saga. And it's an interesting question to ask, what will be left of all this in a million years? What fossils will we leave behind?